Okay, so remember what we're talking about. We have these things called Calderón-Zygmund distributions, right? And we're considering singular integral operators, which we are defining by convolving against a convolving a Schwartz class function. It's defined on Schwartz class function space. It's defined by convolving a Schwartz class function against a Calderón-Zygmund distribution. So there's a bunch of results that we need. We were in the middle of talking about the Calderón-Zygmund. So let me just recall what the distributions look like. So we have these Calderón-Zygmund distributions, and they satisfy. There's a bunch of equivalent conditions. So either you satisfy this pair of conditions, the differential inequalities that like this on the associated function, and cancellation condition that for all Cn normalized functions, normalized functions, the supremum of the distribution applied to the dilated bump function over all dilates was bounded. So that was one way of defining it. Another way of defining it was another equivalent way of defining it was to say that K is tempered. Right? K is a tempered distribution, and K hat is in C infinity away from the origin, and satisfies its own differential inequality. And the third way of defining it, the third equivalent condition was that K is a regular distribution. Such that K hat is in L infinity, and little k satisfies 1a, the differential inequalities above. So those are the three things that we. If you satisfy any one of these Roman numerals, then you satisfy all of them. Okay. So when we're talking about Calderón-Zygmund distributions, we have all these properties at hand. Okay. So we're trying to show the LP boundedness of the operator. First defined on the Schwartz class, but defined by involving some Calderón-Zygmund distribution against the Schwartz class function. And one thing that's going to be useful for us is the Calderón-Zygmund decomposition. Okay, so remember what we did here, right? So we have this Calderón-Zygmund decomposition. We want to split f into these two functions such that, and there's this open set E sub alpha such that the measurement E sub alpha is controlled by the L1 norm of f over alpha. 2, the good function is bounded by C alpha everywhere. And 3, E sub alpha can be written as the sum of QKs, and B will be equal to the sum of the BKs, where the support of BK is contained in QK. The average of BK over its cube is bounded by C alpha, and we have cancellation condition. Okay. Right, and you remember how did we do this? Can anyone, you guys remember how it happened? So we use the Hardy-Little maximal function, right? You take your function, you take its Hardy-Little maximal function, right? And you let P sub alpha be the places where the maximal function is bigger than alpha, right? So that's your E sub alpha, and by the weak type estimate for the Hardy-Little maximal operator, you get this thing, right? We know from before by our Vitali covering lemma that the Hardy-Little maximal operator is weak type 1-1. So we have this thing. And then we saw that, what's G? What was G? So G was equal to F.
If X not belongs to E alpha.
Right. If you're on E alpha, then we.
Okay.
No. If you're outside of E alpha, then we define you equal to F. Right. If you're inside E alpha, then you are the average. You take the Whitney decomposition. Right? You take the Whitney decomposition. Right. And if you're inside, if your point is inside alpha, then you take the average of F over the Q that you belong to. Right. Right. So here's the alpha. It has a Whitney decomposition. Right. For any point inside here, you define G to be the average. G to be the average of F over this thing. Right. Okay. And so we showed already that this bound held, and what we need to do now is show that this last set works. Okay. Right. So right. Right. So right. So we let, of course, B is going to be f of x minus g of x. Right. So what's that going to be? Well. Outside of here, it's going to be 0, right? Right. It's supported on. It's the sum of BKs where each BK is supported in the QK. Right. Each BK is supported in QK, right? And the value of BK, right? BK is going to be the function minus n sub k, right? Right. The value of it'll be the value of the function, but minus the average of the function over that Q, right? And so immediately the cancellation condition is satisfied, right? Immediately the cancellation condition is satisfied because you subtracted off the average. Okay. So so this condition and this condition are done, right? And the only thing we have left is to show that the average value of BK over that thing is controlled by C alpha. Okay. So you say, okay, well, I'm sorry. This should be alpha value. This should be alpha value because otherwise we know it's 0. Okay. So let's consider then the integral of the alpha value BK over its support. Okay, you said, well that's just MF f of x minus mk. Right. Right. And we do a very crude thing. We just bound it by the sum of by this sum. Okay. I'm sorry. This should be very fast. Okay. So we use the triangle equality in a very crude way. Right. Okay. So we already showed that in the last lecture, we already showed that this thing is controlled by C alpha. We already showed that this thing is controlled by C alpha. You remember how we did it? You have this qk, and you're averaging the function over here. You take the nearest point in the complement. Right? You take the nearest point in the complement, call it xk bar, right? And then you say, well, I know that f star at fk bar is in the complement, so that's smaller than alpha. Right? xk bar, f star at fk bar, right, is, right, this is where the Hardy little maximum function is large. This is where the Hardy little maximum function is small. Right? So as long as we're outside, then we're small. And then we use the fact that we have a Whitney decomposition, right? So if we take the cube that contains xk, the distance of that thing to qk is controlled by this, basically the diameter of qk, right? So there's some multiple of the diameter of qk. So this is controlled by, in any case, if we call this thing q tilde, the ratio of this to that is controlled by some constant. Right? And so what does that tell us? Putting this together, we know that the average of f over qk is bounded by alpha. Right? Sorry, let me say it like this. We know that the average of f over we know that the average of f over we know that the average of the absolute value of f over qk is controlled by the average, the integral over the larger cube. Right? You're integrating something positive over a smaller cube, and then you integrate it over a larger cube, so that the value gets bigger. Right? And then we change this to we multiply on top and bottom by the size of qk. Right? Okay, 1 over this times this. Right? And we know that this thing is smaller than alpha. Right? This thing is smaller, so we get this constant, right? This constant times f star at xk bar. Right? But f star at xk bar is smaller than alpha. Right? So we got this done here. Okay. Right? That's how we show that the average is controlled by C alpha. So that gives us, right? That gives us that this thing here is. That gives us that this thing here is controlled by C alpha times the measure of Q, of course. Right. And so what we have left to do is to show that this thing is controlled by C alpha times the measure of Q, right? Because then we divide both sides by the measure of Q, and we get that the average of this thing is controlled by C alpha. Okay, but we do this in exactly the same way, right? This is what we were looking at just now, right? This is the integral of f over qk, right? So, right, we know that the integral of f over qk, if we divide it by the measure of qk, is controlled by c alpha. We just did it, right? So we just use the same result, right? This is controlled by the measure of qk by c alpha. And so that gives us the average of the absolute value is controlled by some constant like alpha. That's just 100. Okay. And so that's the end. That's the end of the Calderón-Zygmund decomposition. So we split our function up into two pieces. We have the good piece and the bad piece. The good piece equals the function outside of here, equals the average of function over cubes inside here. The bad function is 0 outside and equals f minus the average on each cube. Okay. Or it's a sum of functions, each of which is supported on some cube, and equals f minus the average of the function. So those guys that make up the B should be sort of reminiscent of atoms, right? Of the atoms that we saw earlier, and that's what we're going to talk about now. Okay, so sorry, let me. Everything is this. Okay. Okay. So let's introduce the definition. What we're ultimately going to show is a control of the behavior of Calderón-Zygmund operators of singular integrals on atoms. Okay, that's what we need. We're going to we want to apply we're going to apply the operator to this decomposition, right? It will work very well on the good part. That's why it's called the good part. But it will also work on the bad part. Why does it work on the bad part? For the reason that we're about to show, that the Calderón-Zygmund operators actually behave pretty well on the atoms, on functions, as long as they have this bounded support and have cancellation. So that motivates this section. So let A be an multi-function. And B ball. And let's say that if the support of A, so A is supported on that ball, and it has an L1 norm smaller than 1, and it satisfies the cancellation condition. So if these three things are satisfied, we call A one atom. One atom associated with B. And our ultimate goal will be to show the following. That if B star denotes the concentric double, let B star be the concentric double of B. Then there exists a bound A such that for all 1 atoms, for all 1 atoms, the integral of the L1 norm of the Calderón-Zygmund operator applied to the atom over the complement of B star, over the complement of B star is controlled by a constant. So we'll get a control of the behavior of the function on atoms, but on the complement of B star. On the complement of B star. What will we do with the balls themselves? That will be controlled by the Hardy-Little maximum operator, ultimately. Okay. So this is what we want. We want to see how the Calderón-Zygmund operator. So if I say Calderón-Zygmund operator, I mean singular integral operator. This is sort of like interchangeable terms. We want to see how the Calderón-Zygmund operator behaves on atoms, and the estimate that we need is the following. So before we get there, we'll need an intermediate proposition. So let A be a Calderón-Zygmund distribution. Then, for all r greater than 0, the integral of k of x minus y minus k of x dx is divided by a whenever y and absolute value is less than r, if you're integrating over x greater than 0. So this is called the Hormander condition. And often you simply assume that the function, often you simply assume that your Fourier transform of the kernel is bounded, and the Hormander condition, and that's enough for you to get LP boundedness. But we're doing a sort of more even more particular class. Let me actually change this a little bit, because I think we need it a little bit different. We need the statement to be a little bit different from what's in the text, just to use it later. Let me write it like this. There's going to be an x naught in RD. Okay, and you want x minus x naught. You want y minus x naught. Okay. So just a small change. Right. So what we're saying is that there's some ball centered at x naught of radius r. You take its double, right? 2r here, and you're going to integrate over the exterior of the double ball, and your y is going to lie inside the first ball. Okay. So you're integrating y lies inside the ball, and you're integrating over the complement of the double, right? Which is what we're going to need here, right? We're going to want to integrate over the complement of the double of some ball. Okay. So that's the picture, and your x's are all out here. X's all plus that's out here. Okay, so here's the proof. So well, look, by the design theorem, you know that this thing that we're integrating is controlled by the length of y. length of y times the suprema of, hold on a second. Give me 1 minute. So I thought I'd fix this up this morning, but now I see that I'm a little brained. Y minus y naught. Distance of there to there is going to be y. Okay, sorry, I see, I'm just going to prove the statement in the book. I'm sorry, so here's the thing. I think the statement in the book needs to be modified a little bit in order to apply it to here. But now I realize that when I tried to prove the modified statement, actually there's something wrong with my proof. So I'm sorry, but let me just prove the statement in the book, and then I'll show you how we might use it, and I'll try to fix it so that actually it works, but not right now in class. Okay, so we're just going to assume that epsilon is 0. So, sorry, I thought I figured it out over breakfast this morning, but clearly I let something slip. The trouble is that ultimately I want this thing to be bounded by R. Ultimately I want this thing to be bounded by R, right? But if we have this center point here, then this should be y minus this. To get this bounded by R, I need y minus x naught. Right? I need y minus x naught. But in that case, how do you bring in the mean value theorem? How do you bring in the mean value theorem? The mean value theorem should say something like this, right? That the absolute value of the difference over the distance between these guys, but the distance between these points is y. It's not y minus x naught. Right? So this trouble. Okay. Is controlled by the supremum of the gradient of k at z on the line z, where z, L is the line, connecting x to x minus y. Right? You have these 2 points, you take the line connecting them, right? You have these 2 points, you have the line connecting them, and then you have this sort of control, right? That's the multi-dimensional mean value. Okay, so we know that x is bigger than 2r. Okay? The size of x is bigger than 2r, and the size of y is smaller than r. Right? So that tells you that, say that x minus y, right? X minus y is bigger than absolute value of x/2, which gives you that z, absolute value of z, is bigger than right? Because the difference of x minus y is going to be bigger than you've got the distance of x to y, right? The distance of x to y, wait, I'm messing this up too. The distance of x to y
If you think of it as twice the distance of x and y being greater than x, like if you multiply by 2,
yeah.
I think that makes sense.
Are you sure?
No, but I think so.
I don't think so. I don't think so. Let's think about it. Right. So, sorry, maybe this is not. So what we're trying to show is this, that the size of z is bigger than absolute value of absolute.
How is Z?
So z is on the line connecting x to x minus y. Okay. So, right, we want the size of z to be bigger than things like this. At the very smallest, so if you have your, so here's x, right? Right, and you're subtracting off y, right? You're subtracting off y. And so the very smallest thing you're going to get is if y is pointing in the direction of x. Right? That's the smallest thing you're going to get. Any other direction, it'll just get bigger. Right? X minus y will just get bigger. Right? So this is the smallest thing you're going to get. You subtract off that guy, right? And you end up with this thing here. Right? X minus y. Right. So, right. Right. So anybody, right? So anybody on that line is going to be bigger than x over 2 because y is smaller than r. Because y is smaller than r, and x is bigger than 2r. At least, I think. Maybe. Okay, so I think that's it. Okay. So now we use the Calderón-Zygmund inequalities, the differential inequalities, and say, well, okay, we know that the size of the gradient is controlled by some constant z to the negative b minus 1. Right? Because we're dealing with things all involving first partials. Right? But we know this, right? We know this, so this is controlled in turn by some constant times x to the negative b minus 1. Okay. So what does that give us? From this inequality, that gives us that a of x minus 1 minus a of x is less than or equal to y. Y is smaller than r, and then we have this constant times x to the negative b minus 1. So then, if we're integrating this thing, a times y minus kx dx is greater than 2y, well, of course, that's bounded by the integral r x minus 1 dx, maybe I'll totally pop out. X goes in size from 2r upwards. You switch this thing to polar coordinates, right? You get some constant times r. R goes from 2r to infinity. You get this sort of thing. Right, you're integrating. You have this radial function, right? You have a radial function that you're integrating outside of the circle 2r. Right? You have this radial function, right? So you say, okay, I'm going to let r, right? Let r be the size of x, right? You get r to the negative minus 1, but then you need to multiply by some constant times r to the d minus 1 to give you the area of the sphere. Right? You're going to integrate over spheres as the radius of the sphere goes from 2r to infinity. Right? So you need a factor of r to the d minus 1 to give you the area of the sphere that you're integrating. Right? And you get this constant. Yeah, so what I wish were true, what I'm pretty sure is true, is that if you shift this over, then it will still hold, but seem to be messing up a little bit in getting the bound. No. Yes, it's still messed up. Yeah, it's still messed up. Sorry. That was okay. Okay, in any case, we're going to need the one that we can slide around. Okay, so let's just say that we have that, right? And hopefully I'll get it working now in the next class. Okay, so now if you are a Calderón-Zygmund distribution, then your associated function satisfies the so-called Hormander condition. And now we want to show that you behave well on maps. Okay, so let's do the proof of that composition. Here is the idea that suppose you have a sketch it. If you have, let's say that you have an atom. So say A is an atom associated with some ball B. And let's say that X is not in B star. So X is in B star complement. T of the atom at x, this requires a little bit of argument, but equals k of x minus y, ay, dy. The convolution of the kernel, against the function. This is not exactly honest because A is in L2, and so this is actually in terms of a limiting argument, right? How do we define T on L2? Well, we define it in terms with respect to Schwartz class functions first, and then take the limit of Schwartz class functions. Okay, so this is really this is true, but one has to remember what this means. Okay, so right, so this is actually in L2, and so this is really what this means is that you take Schwartz class functions in L. You take Schwartz class functions that approximate A in L2, and then take the limit, and you get this thing. Okay. Okay. So then you use cancellation. This is sort of the standard trick. You have cancellation, so we subtract out from kx. Right. So so T applied to the atom is this integral, right? And we are interested in the integral of TA, over B star complement, right? Like we needed, we're looking at, we needed the x to be in B star complement to ensure that x minus y stays away from the origin. Right? Again, y is in B, right? Y is in B, x is in B star complement. Right? Y is in B, x is in B star complement. And so the distance from x to y is bigger than the radius, right? That tells us that k, big K actually is little k, right? Because big K agrees with little k away from the origin. Right? So we do this. Okay, so we're looking at, now we're trying to get the bound on this, and with the Hormander condition, it's straightforward, right? This is going to be controlled by the integral over B, the integral over B star C, k x minus y and dx. That's the value of a y d1. Right, where y lies inside of B, and we're integrating over the complement of the double. By the Hormander condition, if I can fix it up, this is bounded by some constant, right, by the Hormander condition. Right, and so you get the L1 norm of A, which you know is bounded. So this is bounded by some constant. Is everyone all right? Except for Chris? No, I'm kidding. You may be more all right than anybody in this room, including myself. Okay. Okay, so what do we have so far? right? We're trying to get the LP boundedness of the Calderón-Zygmund operator. We have, from the beginning, we have L2 boundedness, right? And then we have Calderón-Zygmund decomposition, and now we have this control of the integral off of the support of the atom. We get to control our atoms if we integrate, this thing on the complement of the double of the support. Okay, so all these things we're going to need to get the main part of the proof, which is the weak type estimate. Like I said before, once you have the weak type estimate, then you do Marcinkiewicz interpolation.
How do you pronounce it again?
Marcinkiewicz. But in America we say Marcinkiewicz. Yeah. So as I understand Polish, this should be Marcinkiewicz. Not that I know Polish. But in English we say Marcinkiewicz. Marcinkiewicz. So you do Marcinkiewicz interpolation is basically what we did when we proved the Hardy-Little maximal operator's bounds. Right? You remember we interpolated between the weak 1-1 estimate and the L infinity bounds for the Hardy-Little maximal operator by incorporating the L infinity bounds into the weak type bound, the original weak. By incorporating the L infinity bound into the weak type bound, right? And that gave us this sort of strengthened weak type bound, which allows us to get the LP result. So we'll do exactly the same thing. In fact, I regret that we did not prove the theorem in full generality at that time. I was going to assign it. What I really regret is not assigning the full theorem as a problem at that time. Because it was certainly within your grasp. Okay, so the main result, the main part of this is the weak 1-1, the weak type estimate. Okay. Here it is. There exists a bound such that for all f in L1 intersect L2 and alpha greater than 0, the measure of size where the measure of the set where this thing is bigger than alpha is controlled by a over alpha. Marcinkiewicz was apparently was a student of Zygmund, right? So Zygmund was like the parent, the godfather of the field. Right? He's Stein's PhD advisor, Calderón-Zygmund's PhD advisor, also Marcinkiewicz's PhD advisor. Unfortunately, Marcinkiewicz was drafted during World War II and ultimately died during World War II, which Zygmunt, a Pole, considered the greatest loss to Polish mathematics at the time. Okay, so here we go. How do we do this? Well, use the Calderón-Zygmund decomposition at height alpha. Okay, that gives you f decomposes into good part, bad part, right? And of course, this is a linear convolution is linear, so we have that TF is equal to TG plus TB. And so if we want to control the size of the set where TF is bigger than alpha, well, we can control the size of the set where TG is bigger than alpha over 2, and the size of the set where TB is bigger than alpha over 2. Because this set is contained in the union of those sets. Right. If this is bigger than alpha, then it must be that these guys are both bigger than alpha. You know, that one or the other must be bigger than alpha. Okay. So so let's first deal with this first guy. So if we look at this set, size where this is bigger than alpha over 2, we know by that if we multiply this thing by alpha over 2 squared, then that's controlled by the L2 by this 2g squared. This is big changes inequality. So Chebyshev inequality says that this thing is controlled by 2 over alpha squared and the L2 norm equals squared. So this is Chebyshev's inequality. Now we use the L2 boundedness of T, right? We know that this is bounded by the L2 norm of G. Okay. So we're trying to get control on this set. We have that it's controlled by this C over alpha squared as the integral of G squared. Now we're going to break that up into 2 parts. Let's break that up into the integral over E alpha and the integral over E alpha complement. Now on E alpha complement, we have that g of x is controlled by C alpha, right? So if we look at the integral of this thing on E alpha complement, well, that's controlled by C alpha times the L1 norm of G times the times the L1 norm times this, which is, let me just replace this by, I'll leave it like this. So we just take one of them out, right? We've got this thing squared, we've got one of them by C alpha. Okay. Now G on E alpha complement, G on E alpha complement is just F, right? So this equals, and then if we integrate over the whole space, this is controlled by C alpha times the L1 norm. Okay, so, right, that's good, right? So what we have right now is that so this thing equals C over alpha squared times the sum. And we've just shown that this guy here is controlled by C alpha times the alpha over that, right? So that piece, right, this piece is controlled by C over alpha times the alpha over that, right, which is what we're hoping for. There should be enough. Right, otherwise it doesn't make any sense at all. Okay, so okay, so that's good, the control on C alpha. I'm sorry, on E alpha complement, and then on the other part, so let's look at the integral of G squared over E alpha. Well, we're going to be even more crude about it. Right? In fact, what am I saying? We didn't just have this, we had this in general, right? That G, not just on E alpha complement, but on the whole space, G was controlled by C alpha. Sorry. Right? So we'll use that here as well. Right? G of x, the size of G of x is controlled by C alpha, right? And so this is controlled by C alpha squared, C squared alpha squared, times the measure of E alpha. Right. But what's the measure of E alpha? Right. E alpha is where the Hardy-Lilith maximal operator is greater than alpha, and we have the weak one, we have the weak time estimate for the Hardy-Lilith maximal operator. Right? So this is controlled by so the size of this thing is controlled by some constant over alpha times the L1 log f. Right? And so again, we get some C times alpha times the L1 log f. Right? And so both guys, right? So both of these guys, so this gives us C over alpha. Both of these guys are controlled by C alpha L1 log f. And so we get this one. So, right. So, right. So we get, so we have altogether, this thing is controlled by A over alpha, L1 and then the next thing we need to do is show this part for the band function. Okay. I'm really sorry. That's all I prepared. That's all I prepared for today. We'll finish this up. We'll finish up the proof of this next time. So. I hope you don't feel that you're not getting your money's worth. Try to cram a lot more into the next lecture, just to make up for it. Any questions? Any questions? Okay. I think this is pretty straightforward stuff compared to some of the more delicate stuff we've done. This is more straightforward, just estimates and balance.